Okay, so glycolysis. Glycolysis is complicated, but once you understand the main steps and the parts of each step, it's not that complicated. So glycolysis is the first stage in cellular respiration, and it occurs in the cytoplasm of the cell. Basically it's a breakdown of glucose by enzymes, and they release energy, and pyruvic acid releases energy for cellular metabolism. So basically glycolysis has three main stages. So the first stage is actually, out of the 10 steps glycolysis has, stage 1 is steps 1 to 3, and stage 2 is stage 2 is steps 4 and 5, and stage 3 is steps 6 to 10. So starting in stage 1, it traps glucose in the cell and it destabilizes its structure. And we're gonna see in a little bit what each step in stage 1 gives in the sequential order of glycolysis. Stage 2 breaks down the glucose into smaller components. And again, it was steps 4 and 5. And stage 3 harvests the energy to form ATP molecules and pyruvates. So first we start in glucose, as you can see here. So glucose, glucose is a transit. From glucose to glucose 6-phosphate, you need a transferase. So it requires a divalent metal atom to function, such as magnesium with a +2 charge. It interacts with the ATP molecule, and the domains rotate 12 degrees inwards, so it creates a perfect induced fit. So for the transfer from glucose to glucose 6-phosphate, you need a hexokinase. And the hexokinase catalyzes the addition of a phosphoryl group from an ATP molecule. So hexokinase, for example, hexosugar, an example of a hexosugar is glucose. So then when you get to glucose 6-phosphate, you see the phosphoryl group is there. So to trap the glucose in the cytoplasm of the cell, that's the one reason for why the phosphoryl group is sitting right there. Another reason is that it makes it polar and it gives it a -2 charge. So the membrane transporter that brought glucose can no longer bind. So it's basically trapped and it can't leave the cell. And the third and final reason why there's a phosphoryl group is to destabilize the structure. By destabilizing the structure, you increase the energy, and this makes it more reactive and more likely to undergo glycolysis. So now from glucose 6-phosphate, you go to fructose 6-phosphate. And that step is step number 2 from stage 1. So step number 2 is an isomerase. And as you can see, you need a phosphoglucose isomerase for that conversion. So the phosphoglucose isomerase transforms an aldose to a ketose. It also opens up the structure to form an open chain conformation to expose the aldehyde group. Then you catalyze the previous step to fructose in an open chain configuration. And then you transform the previous step to a closed cyclic chain. And then you go from fructose 6-phosphate to fructose 1,6-bisphosphate. And there you need a phosphofructokinase 1, which can also be called PFK. So for that the phosphofructokinase 1 adds a second phosphoryl group onto sugar. And this commits the sugar to glycolysis, basically. And step 3 is a lyase. Remember, step 1 was a transferase, step 2 was an isomerase, and step 3 is a lyase. And then here's where it gets a little bit more complicated, that you transfer from fructose 1,6-bisphosphate to dihydroxyacetone phosphate, which can also be called DHAP, but also you transfer to glyceraldehyde 3-phosphate, which can also be called GAP or GAP. So the glyceraldehyde 3-phosphate lies directly on the glycolytic pathway. So it can go directly to stage 3 of glycolysis without further change. But the hydroxyacetone cannot, it can't go to stage 3 without a change. It needs a change. And to prevent the loss of energy potential, the DHAP must be transformed into GAP. So the DHAP, which is this, the hydroxyacetone phosphate, needs to be transferred into that so that glycolysis can proceed. So triophosphate isomerase, it can also be called TPI or TIM, catalyzes the rapid and reversible conversion of DHAP to GAP. So remember, we have to convert one to another so glycolysis can continue. So for example, the DHAP starts with a 96% concentration, and GAP has a 4% concentration. So, and that would be a problem. But according to Le Chantilly's principle, it's not a problem because DHAP will be used up in stage 3, in the next stage. This right here is also it's also an oxidation reduction reaction. Oxidation reactions. It's an oxidation reaction. So it goes from a ketose to an aldose, from a DHAP to a GAP, like I said before. TPI, which was triphosphate isomerase, it does this via an intramolecular redox reaction in which a hydrogen is transferred from carbon 1 to carbon 2. And then the anidyl intermediate is formed. So this right here, the glyceraldehyde 3-phosphate dehydrogenase, that basically catalyzes a transfer of the hydride group from one molecule to another. Remember that the hydride group is an H atom with 2 electrons. And then this is used to make 1,3 bisphosphoglycerate, which can also be called 1,3-BPG. And then here in this step, where 1,3-BPG is converted into 3-phosphoglycerate, ATP is produced. And phosphoglycerate kinase is needed for that conversion. And remember, this is a transferase, unlike the previous one. So from 3-phosphoglycerate to 2-phosphoglycerate, you need phosphoglyceromutase. So basically, this catalyzes the transfer of the phosphoryl group from the third carbon of 3-phosphoglycerate, remember the third carbon, yeah, to the second carbon to form 2-phosphoglycerate, because the 2 of the second and the 3 of the third. So it goes from the third carbon to the second carbon. And this reaction actually, it requires, like to say, catalytic amounts of 2,3-bisphosphoglycerate. And the 2,3-BPG is used to keep the catalytic histidine residue in its active phosphorylated state. So in the first step, a phosphoryl group is transferred from the modified histidine onto the 3-phosphoglycerate, forming 2,3-BPG, like I said before. That same histidine then removes the phosphoryl group from the third carbon, forming the rearranged 2-phosphoglycerate. Then comes the 2-phosphoglycerate, yeah, which needs an enolase to form a phosphoenol pyruvate. So this is actually a dehydration reaction. It increases the phosphoryl transfer potential of the molecule, which makes it much more likely to donate one of its phosphoryl groups to ADP. And then phosphoenol pyruvate is created, which can also be called PEP. And then you need a pyruvate kinase to create a pyruvate in the enol form because of the enol in the previous step. So since you need the pyruvate kinase, the pyruvate kinase basically catalyzes the phosphoryl transfer from the high potential PEP molecule onto ADP. That's what forms pyruvate. And then you go to the enol pyruvate enol form, and then to the pyruvate kinase, which the pyruvate kinase is thermodynamically more stable than the enol form. Okay, so that's the basis of glycolysis.